No, she's going to help us. It's the last
Oh,
welcome.
yeah.
No.
Right. Come on. Lydia.
Come here, friend. No,
Come on.
It's good for these students to meet them.
Ways to find out where this classroom was.
Ready?
Ready?
It's
Okay.
magical time.
Ready? Magic time?
Everybody, last class.
Last class.
Ready?
Welcome! EECS16A! Woo!
Every class we do this.
All right.
This is Professor Lydia Son from Mechanical Engineering.
That's right. Wow, can you believe it, Anna?
I can.
Anna, can you believe it? Can you believe it, Anna?
Mickey, I can.
You can, Anna?
Uh-huh.
Wow. Third time a charm.
I know.
Yeah?
Let's see if we were better.
That'll be the last time we ever teach 16A.
Together.
So, oh, no. Don't say that. What? Looks like she's going to teach it again.
I will.
With somebody else.
With Laura.
What? You know what? I'm going to teach it with Ricky.
Great.
Yeah.
Yeah,
there you
it's
go.
good to mix. And then
Yeah, I don't want to.
we'll
like
miss
you
each
stay
other
over
so
there.
much
I don't want
that
everything.
then we teach again for 5
Right.
semesters after that. Announcements. Midterm 2 grades are finally out. We did it. It took a little bit longer given the circumstances, but it's there. Average is a B, so not bad. Okay.
What?
That's all the announcements that I had.
Oh, we're going to this concert.
Oh yeah, we're going to this concert. Saturday. Ah,
All right.
we're going to celebrate and dance.
What did we talk about last time? You weren't here.
I was not here. I
But
was
did you watch
writing
the
a
video?
proposal.
That's pretty good. Did you watch the video?
I did not watch the video, no.
It's pretty good, right?
Was
pretty
it good?
good?
Oh, okay.
Yeah? Was it good?
Okay, let's do
Did
it.
they actually ignore me?
They're agreeing?
No, they're not. Like, they're just ignoring.
They're
not even
watching the
responding.
World Cup. Anybody watching the World Cup? Oh,
Right now?
update
Oh,
me
oh,
on.
so we wanted
It's
to do
so
this.
exciting at the moment.
So should we pretty much pause this lecture for 20 minutes? to just watch the end?
Japan is winning. Japan is still winning, and Costa Rica and Germany are tied 2-2. So, still there. I'm getting updates.
We'll give you updates.
I'll give you
when we're
updates.
done. Some of them are just watching it.
It's very exciting.
Okay, so I think last time we talked about applications of least squares.
Mm-hmm.
Applications of least squares we talked last time.
Okay.
And what we're going to do this time is going to do a little bit something else. We're going to, I had Lydia coming over here because one of the reasons is Lydia and I have been working for a long time now, about 8 years or so. Eight years. And we came up to a really fabulous research project, and I just wanted to look at some of the things that we looked in, and with your knowledge in 16A, try to come up or at least figure out, what would you do in certain situations. So we're going to introduce to you a kind of a problem. We'll think of it from a circuit point of view. Then we'll think from a signal point of view of how you go and solve that problem all together. And I think it ties up pretty nicely the first, second, and third module of this class. And I think there we're going to, end the official material for the class, and then we're going to give you some overview of a little bit about what we've done in the class and what's next and what also both of us are doing for a living, except teaching this class. So, yeah. All right, so I want to describe a certain problem. And the problem, it's called resistive pulse sensing. And resistive pulse sensing, also known as Coulter counter, the ideas behind this actually goes back to the 50s. This is actually how a lot of the blood counts are being done, and now actually DNA sequencing is done using some of those ideas that are going to be presenting today. But one of the stuff that Lydia's group is doing is look at cancer cell characterization at the cell level using these microfluidic devices. So here's here's a scenario that I'm introducing you from a device point of view, that we would like to be able to sense cells or particles going through some really tiny device and be able to learn things about them. So here's a glass slide that you deposit electrodes onto it. There's 4 electrodes here, 1, 2, 3, and 4, and these are pads that you can actually connect a voltage, a current source, or a voltmeter, ammeter to sense the whatever is happening. Then you go and deposit this PDMS. PDMS is pretty much silicone, patch that is embedded in it is this really microfluidic channel. What does it mean? It's a small channel at a microscopic level, so about 20 microns wide, about same height, something like that. You can design them to be different sizes. And then you have this inlet and the outlet, and you go and flow stuff in. It goes through the channel and then comes out on the other side. Okay? So normally if you flow fluid, then it's fluid going there, but you can put particles in it. You can do all sorts of interesting, like put cells, live cells, and so on and so forth. Okay? And we would like to be able to detect or see parameters of the thing that's going inside. Okay? Up to here? Okay? Good. It's good problem. Now, what we're doing is we're connecting those pads from the outside to a current source, and we will then measure the voltage or the potential differences between those 2 pads in the middle. Okay? So what is the first thing that you think about? It's like, well, I connect a current source to something. Obviously, current source has to go then the current, like it actually forces a current. So we need to have some medium for the current to flow, and that medium is some cell, culture material, PBS, I think often it's used, something like water with some ions that would conduct then electricity. And so how do you think you can then model this part of the channel? I mean, we put in a current source, current is being pushed into this, and then, comes back out here. How do you model then that channel, that fluid channel? What? Speak up. A resistor. Absolutely, right. It has a certain resistance, right, to the flow, right? Because, whatever fluid there is, it's not a wire. So we can absolutely model it as a resistor. So this is what's called also resistive pulse sensing, because we're actually doing that. So we put some current in, and then, of course, that will force the current to be at a certain level. There is some resistance here, and hopefully, obviously, there will be some potential between the middle 2 pad, which we can then sense. Okay? And we're going to mark those pads as U1, U0. These are the nodes. So U1 and U0 that we'd be then measuring. So here's kind of like a side view, or a top view of this device, a little bit more simplified, not in 3D. So we got this device, and then we have this electrode, and another electrode here, and this is another electrode, this is another electrode. This is a pore, this microfluidic channel, and then current's being forced through this electrode into the fluid, then it flows through here, and then comes back in this circuit. And then we are sensing, we want to see pretty much what is the potential between U1 and U0. And according to Ohm's law, the potential would be U1 minus U0, the difference, would be then I0, whatever we're putting, times R, which is the resistance of that channel. Okay? Does that make sense? So we can think, if you remember, when we modeled a resistor, we looked at its width. It has like a certain intrinsic resistivity, and then based on the width, the height, and the length, we can calculate what would be then the resistance of the entire channel, right? So you can think of this modeling, that type of a device, as maybe a series of resistors that are, one after the other. Can we kind of think about that? Is that a good model? That resistor is connected in series? I mean, if the channel is also very thin, right, so yes, you can also put some in parallel and some things like this. This is how we calculated it. But think about each piece of this channel as being a resistor and then in series connected to each other. Is that a good assumption? And I would say that each one of them would contribute some delta R, some delta resistance. And overall, when you sum them all together, you get the resistance of the channel. Okay? All right, that's great. Ooh, now, see this dot over here? That represents maybe a plastic colloid, like it's small, kind of a plastic sphere that sometimes you put through these type of things, or it could be a cell. It could be any particle that you would want to flow through the channel, and that would be this red thing here. And the question is, what happens when we start flowing stuff in? So right now we measure a certain amount of voltage, and that voltage depends on the resistance of the liquid. Now we're flowing a particle in. And the particle kind of flows in, displaces a little bit of this water, but it's a very, very small particle compared to the entire channel. And the question really that arises is, how do we model this particular case now? Because we want to see what the effect of this particle going in. Now, let me tell you a little bit about it. Let's say this particle is plastic, or let's say this particle is a cell. Cell membrane is made a lot of fatty tissue. It's fatty molecules, so it's actually non-conductive. So it is a dielectric-like material. Okay. If it's plastic, of course, it would kind of you see what it's going to do. It's going to maybe block some of the water over there. So what do you think would happen? How can we model this? A capacitor? It's interesting, but let's say it's not complete. I mean, it's still connected, right? Like there is some stuff over there. It's not completely. I mean, let me argue that it actually has also resistivity, but because of the way it is, it's not it's just not a conductive fluid. Then, would you say that if I can model this as a higher resistivity, that would just be put inside the channel now? Some large resistor that would prevent current from going at the rate. Yeah. The particle is a kind of similar size of the channels, like it's kind of touching maybe almost the edges, but it's just displacing some of the water over there. So it's kind of like removing some of the water, which are very conductive, but it by itself is not very conductive. So can we say that we actually do something like this, where we effectively stick some, in series, we stick some big resistor over there? I mean, is that exactly what is happening? Yeah, maybe, but like it could be modeled at that. Maybe this is a good approximation to what is actually going on. Okay? Think about having a wire that's it's like semiconductive, and then you kind of like remove some of that wire. Now it has less width. Well, that wire will have more resistance at that particular point, right? So that's kind of what's happening here. When this particle displaces the water, then that part of the channel becomes less conductive. Okay, does that make sense? Okay. So how would our circuit model then look like? How would it look like? Well, I used to have R over here. Suddenly, I stick in some, and this R is based on a lot of these small delta R's. Now you've got like a big delta R in between. So what happens to your resistor? It goes up. Yeah, it goes up. How? How is it connected in this model? In series. So in series, how would resistances sum? So maybe I can think of a model of something like that, where I've got, the potential differences between those two nodes is this I0. Still I0 is flowing because we have a current source, times R, which was the resistance of the channel. And yeah, maybe that is, changed a little bit just because this is displacing. But, whatever was changed, I can just add R cell to it. So it's kind of, it compensates for it. So it's a still pretty good model, that adding the resistance of the cell to the resistance of the original channel. Can you come up with a slightly better model? Maybe, but this is relatively good. Okay, just because of the size, it doesn't really displace a lot of water in the length. It displaces water in the width. Does that make sense? Okay. So now I want to measure my voltage as a function of time. So the cell was originally outside of this device, right? So then the resistivity was R. And then when the cell eventually moves in, then the resistivity goes up. What would happen to the voltage? What happens to the voltage when you have I0 times R and R plus R cell is bigger? What would happen to the voltage? Increases. So can we draw a graph of the voltage as a function of time, depending on where the cell is? Can we? How would it look like? Yeah, you want to? How would the location? Okay, so does it matter from a circuit, like from our model point of view, if the cell is over here? It does? It's what? So no matter where it is, it's just still going to be in series, right? So it doesn't really matter where the cell is in the channel. As long as it's in the channel, it will still have exactly the same resistance, the entire channel, with the cell. Okay? When the cell is outside, the resistance is lower. Okay? So the voltage is lower. So how would the graph look like? Do it with your hand so I can kind of see. Yeah, some like square or something, right? Like a square pulse, right? This is also what's called resistive pulse sensing. So we'll see something like this. As a function of time, we'll measure some voltage, and then suddenly the cell will go in. We'll see a jump in voltage, and then straight, and then down, and then when the cell goes out, and then just go back to normal. Pretty cool. So this is called Coulter counter. This is how they count blood cells, for example. Super nice, right? Like you flow blood cells through this small thing, and then you count them. Can you think of a circuit with a comparator that you could kind of do that? Yeah, right? Like you could come up with something with even like a small Arduino, a MSP430 that would connect this kind of device, and you'd be able to count cells, right? Can you imagine that? Ah, that's pretty fabulous. Okay, so then the cell comes out, and then that goes away. Okay, so that was interesting. So here's one of Lydia's student. So it's combining Lydia and Studia. One of Lydia's student came up with, and here's a slightly different channel design. And this different channel design kind of looks like here. This part over here is called a pore. That's the same width as in height as before. And then you stick in this wider region of the channel. You just design the channel to be a little bit wide over here. They call it a node. And then after that, there's a pore. And then the question is, kind of, what is going on here? sorry. What is going on here? How would I model this device? And in addition to this, and in addition to modeling this device, I want to see kind of what would the pulse look like. Okay. So now when the cell is in this place, I would say, oh, I got some resistance of the, of the part of the pore, right? That would, the same R as before. I've got R cell that is in series to it. And then I've got the node, which is wider. Node that is wider, what, I need to go faster? Is that what you mean?
Yes.
I need to go faster.
Want to interrupt.
Oh, go ahead.
I didn't want to interrupt.
But what does he mean? Like I need to go fast?
It's just no time left.
Oh.
But go ahead.
It's like an hour.
Japan led the group, by the way. And Spain went through for World Cup followers.
What time is it? Like, it ends in an hour.
Okay, Mickey, go.
Okay. It's planned. It's the same thing that there was planned before. Don't worry about it. I'll give you as much time as you want, except the time that you don't get. Okay, so then, so you got this, resistance in the pore, you got the resistance in the cell, and then you've got resistance in the node, which is different. What it is, higher or lower? It would be lower because it's wider, right? It's wider. When your resistor is wider, then it actually conducts a little bit faster. Okay, so this is the point here. The cell goes in, and then impedance goes up because the cell is inside. Now the question is, what happens when the cell enters the node? Now it's wider. So how would you model this if you think about it? How would you model this? I mean, now these are in series for sure. They're in series with this part, but how's this cell related to the resistance of the node? What would be a good model there? Think of current kind of flowing, right? Any ideas? Yeah. In parallel maybe, right? That's the interesting thing. So maybe I can, these are all resistors. Here we have a big resistor. That's a big one. But all the other ones are a little bit smaller, right? That are in parallel to it. So effectively, I've got myself an interesting model now where in the node part, my resistances are plus R cell in parallel to R node. Is that exactly what's going on? No, but it's a good approximation. You're doing it in your head, and so okay. So what would happen? Now you got a lot of very high low resistance stuff in parallel to a high resistance stuff. What would be the overall resistance? Increase or decrease compared to the cell? Decrease. Think about it. Let's say you just would put wires that are fully conductive, no resistance whatsoever. A current will just bypass, and the cell would not even exist there. If you have water around, yeah, there is some resistance there, but it's still much lower than the one of the cell itself, right? So when I put a low resistance in parallel to a high resistance, the dominant part is the low resistant. That's where the current will like to go, the least resistant pathway. Okay? All right. So then going through here, what we'll see is that the voltage across the entire thing, because this thing is lower, will then go down almost to the level of the original one, but maybe a little bit higher than that because the cell is still there. Okay, so the voltage will go down, and then once the cell gets into the pore again, then the resistance will jump back again to this model, and then we'll see another pulse coming. So now, by creating this device, we have these two pulses. And we know exactly when the cell is in the first part, and we know exactly when it's the second part because we've got this kind of intermittent pulse in between, which is very interesting because you could do all sorts of stuff here and here. For example, you can put some antibodies maybe over here and maybe not put them there. And if the cell interacts with the antibodies, it will slow down. And if it'll slow down, maybe this will be a little bit longer because it takes more time for it. So you'll be able to say something about the cell properties. Right? So you could do all sorts of interesting things with this type of a device. Right now, we're just trying to model it, though. Okay, so saying that, here's some complexities. Let's say you have this type of a device where you've got these two nodes over here, 1, 2, and we have a cell that wants to go through. What do we expect that signal to be? Well, the cell will go in, we get like a higher pulse, lower pulse, higher pulse, lower pulse, higher pulse, and that's it, right? So we'll get something like this. The cell moves up into the pore, gets into the node, pore, and then outside. But what happens when you have what's called a coincidence effect, where more than one cell enter the channel? If the channel is long, then you can have more than one of them. What would happen there? Let's say one is here, one is here, one is here. You would get kind of like different changes of this resistance at different time points, but depending on where each one of them are. And so the signal that you're actually going to get is going to look more like that. Now that's a little bit more complicated. What happens? The signal, I mean, we're expecting a signal like this that we can then interpret and learn something about the cell. Now we're seeing something like this. How do we call that effect? Remember from the satellite's point of view, for example, in GPS. Interference. You've got some signals from different sources interfering on top of each other. Right? They're interfering, so we're unable to then maybe use the knowledge that we have about, maybe figuring out all those kind of timing and things like this, or the size of it. You know, they're kind of overlapping. It's hard for us to see. They interfere. Okay, so what can we do? What can we do when you've got stuff that is interfering? What did we learn about the type of signals maybe that are good, that perhaps, I mean, how did we deal even with this when we had, satellites? Like in the GPS part, you've got 20-something satellites being transmitted at the same time. How can we figure out the signal coming from which? You try to make them orthogonal maybe, but we said that orthogonal is possible for an inner product, but how do we detect something? Like how do we detect, for example, a particular shape? How would you detect a particular signature? What did we do in the timing when it actually goes through? Cross-correlation. So we know the signal we're expecting, we could do perhaps cross-correlation. Now what are the properties of good codes for cross-correlation? I mean, we can do cross-correlation with whatever we want, but that may not actually result in something that will be effective. What is a good, effective code? Yeah?
They have to be
As
as close to orthogonal features as possible.
close as kind of orthogonal. What does it mean, a cross-correlation of something being close to orthogonal? So it should, we also took the notion about autocorrelation, right? The correlation of the signal with itself. What is a good code in that particular case? Because all of these would be pretty much the same, yeah. So at 0, it should be very high, and then the rest would kind of be low, right? Remember that when we talked about the cell lines? What's a good property? And so maybe we can actually design the pores and the nodes such that we get this type of a response that looks like something that would have an autocorrelation that has the nice properties. Okay. You can probably now imagine yourself thinking about that because, oh, somebody's posed this, oh, how can you separate the signals here, the overlapping? Well, let's do cross-correlation, but hold on. It's not good to do cross-correlation with this kind of a code because this one of a code, like when you try to overlap, it actually overlaps quite a bit with each other. So instead, you can think of ideas like, for example, Barker code. Barker codes, we learned gold codes in class, but Barker codes actually are codes that are designed for sequences between 2 and 13. There's no more than 13. But these are kind of the sequences, and they're comprised of plus minus ones, and this is what's called a Barker 5, this is a Barker 7, this is a Barker 11, where you have area where this thing is high, so it's a 1, 1, 1, minus 1, 1, for example, for Barker 5, and so on and so forth. These have very, very nice properties of autocorrelation. Actually, they're optimal in a certain way. And the optimality is that when you actually compute the autocorrelation of a Barker code, so a Barker code with itself, you see that it has, if this Barker code is length 7, there will be 7 at the peak, and then the side lobes, or whatever it's, all the shifted one, will only be as high as 1. That's the only codes. Barker codes are the only codes that provide you. Gold codes, for example, are never, if you have a 10,024 length code, then the autocorrelation will be 10,024 high, but the side lobes will not be 1. They'll be greater than 1. Barker codes are the only one that would be length 1. So that's a very high peak to side lobe ratio. So that's great. So if you have then a signal, and we want to do then a cross correlation with a Barker code, you see that once it moves and overlaps, this is the correlation. You see how it kind of matches this one, so it goes high, and then it kind of keeps going. And once you do a cross correlation with a Barker, in this particular case, I think Barker 7, you'd see peak, 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 and you know exactly at what time point that cell showed up. And you can separate the signature of the cell. Pretty cool. So these are kind of the cells overlapping on top of each other in terms of their signatures. So interfering, but now through cross-correlation, we're able to then remove that interference. Okay, so that's ideally with a Barker code with plus minus 1. Now, the problem is, with resistance, you cannot decrease it. Like, I cannot have a cell with lower resistance than, it's just it's not gonna, it's gonna be a problem. We're always increasing the resistance. So it's never going to be negative, right? So there's just no way for me to become negative. So what we could do instead is think of other codes that are just single-sided that behave maybe similarly. And the idea here is what's called to take these codes of 1, 1, 1, minus 1, and 1 that have this autocorrelation and do what we call Manchester coding. And Manchester coding translates a 1 into a high-low type of a signal and translates a minus 1 into a low transition to high transition. Okay? So a 1 is a high to low, another one is a high to low, another one it's a high to low, and then this is a minus 1, so it's a low to high. And then it's a 1, so it's a high to low. And the autocorrelation is not as nice, but it's still pretty good. It has a very sharp peak, it has a negative side lobes here that are a little bit bigger, but overall, it has pretty nice performance of the autocorrelation point of view. So another question, and that was actually a key, is how you make cells talk like that. Ooh, 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 ooh. Like how you design them to speak Barker. Like the cells need to speak Barker. How do you do that? You place the nodes and pores in a particular way that would generate something that looks like a Manchester-coded Barker code. Okay, so how do we do that? And this is the work of a few folks, but we've got a nice paper that was published on this. And here's an example. A Barker 5 would be a plus 1, plus 1, plus 1, minus 1, and 1. That's the code. We encode that into a 1, 0, 1, 0, 1, 0, 0, 1, 1, 0. And we want to implement that in a channel, in a physical channel. So how do we do that? This is the signal that we want to get. We want to get a high, low, high, low, high, low, low, high, high, low. How do we create a channel? Well, when you need to match, kind of whenever it's high, we need to have a narrow channel. Whenever it's low, we need a wider channel. Right? So we can design this device. This device will have a pore, which is a narrow channel, where the high signal is going to be when the cell moves through. And then it's going to be wider when the cell goes through it, so the signal is going to go down. And then high, and then again down. And resistance will go high, down. In this case, it will be a little bit longer, and then also a little bit longer in this area because of this changes. It's pretty nifty. So think about that. From a circuit point of view, we kind of realize, oh, you could do all sorts of interesting stuff, do resistant pulsing. Then if you want to actually be able to detect all those interferences within the case of interference, so what do? Well, you can actually modify the channel through the idea of cross-correlation, autocorrelation that fits. Take idea from communication, from satellite communication, from GPS, and then use them to design a new fabrication of this PDMS channel that would spit out a Barker code-like sequence we will then be able to go and detect. Here's our actually cells. These are cells that went through a channel. These are their signals. Can you see the Barker code there? It's pretty cool, right? And then you go and you take this real data and you say, oh, you know, based on how they go, this is a 26 millimeter per second type of a pulse. This is the width. And then you do a cross-correlation with those signals, and you see, oh, wow, it matches this really nicely, okay? And if you look at the correlation plot, you see, oh, there was one here, and there was a one here. That kind of looks okay, kind of weird. And this one, okay, I kind of detected something, but not perfectly. Why this was detected perfectly and these weren't? You see what happens to them? They were stretched. There's just different cells or different particles may go actually at different speeds. If they go at different speeds, then the whole signal kind of stretches out. And when I try to do cross-correlation with a particular signal, then it's not going to fit as well anymore. Any ideas how to solve that problem? Expand. So maybe do cross-correlation with different codes that are just a little bit expanded versions of them. And if you do that, then I can do this cross-correlation with all of those and see, oh, they fit nicely. And now I also detected the speed through cross-correlation. I detected the position, the time, and the speed of those cells. That's pretty cool. Now I can actually draw it in a two-dimensional space where this is the velocity, and this is the time, and the intensity shows the cross-correlation result. And I see, oh, yeah, I've got a cell here. This is a cell that was at about 26, I guess, millimeter, 24 millimeter at that point appeared. And I can kind of mark it. This one is also a high one that appeared at this time point, but it's a little bit slower, or sorry, faster, I guess. And this one, again, I guess this direction is slower. Okay, so then I detected those three cells, and I can see their signature by looking at the peaks of this autocorrelation that is now two-dimensional because I do a lot of those codes. So in some case, if you think about the satellites, that also I tried many codes there, right? And then I could have potentially also plotted that as a two-dimensional plot. So that's pretty nifty. So, yeah. Oh, because how you stretch them depends on the velocity. So if this is wider, that means that it's slower. It takes more time to go through, so that your pulses are kind of stretched. Does that make sense? Something that goes fast will oscillate very fast. Something that goes slow will kind of like, right? So you can get the velocity out of that. Okay? Cool.
Question.
Oh yeah, I was just gonna ask, is it because we changed the cells, or are the nodes and the pores themselves like made of different material?
You can play with a lot of stuff. I mean, this is all the magic about, also the chemistry and the biology of how you do all sorts of things. But in general, the way we sense is resistive, right? But we can change also the sizes to adapt them for particular cells, cell sizes, do all sorts of nifty stuff. That's the design of the device. That's where the kind of a cross-domain knowledge is useful. If you know a little bit, you know the biology, maybe the chemistry, the electrical engineering, you can come up with something together that would let you do the sensing that you're interested in. That's where domain knowledge is very important. We just wanted to show you that the concept of satellites can also be used for example, for detecting cells, and how to design even those channels to detect those cells. If you're interested, talk to me and Lydia, because we're definitely looking for folks to, do some research in this area. So talk to us.
Really?
Yeah.
Even after this class, they can do the research?
I think so. I think they'll have knowledge in order to do at least some of that. Yeah.
Of course,
absolutely.
of course. So much. Yeah.
Okay, folks. You did it. Congratulations.
Yay!
Finally, it's the end. Except that you still have a final to go through. So what we wanted to do in the next 35 minutes is to talk a little bit about kind of what we've done, and then want to talk also about some of our work that we're doing. So if you just remember, this was all the stuff that we talked in the beginning. Pretty cool. Now you can kind of look at those like, oh, wow, that's funny. That's so funny. And all that stuff, right? Do what? You don't get this? It's an op amp with like capacitors and resistors. You can figure out, you can do an analysis of this, what it does. Here's what you've done in the class. You build a camera, a weird camera, but pretty cool camera. You made a touchscreen, and hopefully some of you will also do the APS lab, which is localization, to understand how localization is actually done. Again, highly recommended. Highly recommended. That will absorb the idea of correlation, cross-correlation, recovery, least squares over here. If you go back to imaging lab 1, I mean, what are there? I mean, like we showed you a lot of stuff. There was the sensor, we've got the analog circuit, we've got the analog to digital, and then the post-processing. Here, the solar cell or the photodiode for you was really just can be modeled as a current source. So once you realize it's a current source, oh wait, I kind of know what's going on, right? What about that? You want to know about solar cells? What do you do then? If you want to know about solar cells, take E134. Yeah, take E124.
I don't do finals in my class.
We also put a capacitor here. Why do we put a capacitor? You don't know where we put a capacitor. We told you like this is a bucket or something like that. I don't know, in lab. Yeah. And you believed us. Well, take 16B. Understand the transient response and how capacitors actually smooth and filter out transient responses. Okay? Analog to digital, like converting some signal and sampling it, like we just assume that's possible. Well, how do you design one? 16B. 16B will learn how to design one. What about all the post-processing that you need to do in order to make a camera? Well, all that, you got all this 120 series. And then if you want to even take it further, do detection, classification, learning stuff, CS188, 189 will be excellent classes to understand. And then, of course, if you want to do that, all the programming, understanding kind of what's going on, the architecture of these processors, the architectures inside, how you make those chips, right? Program them, look at integrated circuits, analog integrated circuits, digital integrated circuits. This is all kind of built in to make devices that are tiny, tiny. Now everybody of you is kind of holding it themselves. A lot of interest from industry because there's a huge need right now for designers of circuits. I mean, it's just like Apple is pretty much paying
begging
us
students to take these classes.
to take all the classes, so we'll be able to hire people that are having a hard time to
And
find.
you can learn how to make these devices in 143. You actually go to the lab and make some IC.
Let me just skip a little bit some of these things, because Anna is complaining maybe that
That's
I'm
right.
just talking too much. And I'll just let Anna talk about what she loves talking about, which is
What to do next?
start with that.
What did you...
16B. No, really, 16B is a great class. What you're going to do in 16B is pretty much learn advanced circuits topic, advanced control, and also advanced signal processing and some machine learning, that you'll be able to create something that is this robotic car that you'd give us voice command. It would hopefully do something for you. We have a video of this.
Banana.
I think we have a video.
We had last semester.
Yeah.
Oh, there you go.
Say hi, I'm Kenny.
Hi, I'm Eli.
We're in the Monday 2 to 5 lab section with Eric.
And this is our car. His name is Jeremy. And the 4 words we chose are wheels for going straight far, lasagna for left, ziti for turning right, and parmesan for short forward. Do you want to explain where our words came from?
Yeah, so Jeremy's Italian. He's representing his country with his little Italian flag, and he's the first Italian electric vehicle. And so he's going to demonstrate his skills for us today.
Wheels.
Woohoo! So you see all the poor sobs, in the first floor of Corey. Banana.
That's it.
That's gonna be you.
Parmesan.
Ziti.
All right. So there's a lot to it, right? First of all, to making a car go straight by controlling different motors, right? That's not trivial, okay? Or turn. It's just not a trivial thing. You have to know kind of how to control those such that it will go and turn how much you want and change direction and go. Because this is not a wheel that is moving, it's actually just controlling the speed of those, right? And then, of course, the detection, classification of the speech, this circuitry that you'll build there using op-amps and filters and so on and so forth in order to be able to do that.
And great instructors.
Great instructors.
Ali and Kanan, I think.
Oof, wow. Wow.
I know.
Oh my
It's
God.
good to
Oh,
get-
this next semester is just like
Yeah.
this came from like the heavens. the
I know.
instructors.
We should take 16B
I
next
should take
semester.
16B
It's
with
going
them.
to be
Yeah.
amazing. Yeah.
Kanan and Ali? Oh
Uh-huh.
my. Oh,
Can you
wow.
believe it?
Wow.
I know.
Wow. You're in luck.
Yeah.
So take 16B. Oh my God. I mean, from 16A, there's a lot of things that you can then go and take. If you like design and thinking about design, you can go through the circuits part, like 105, devices, 61C, for example. On the modeling part, you got all this linear algebra that you learn, the control system signal processing, and then that uses a lot of probability. So 70 and 126, those are amazing classes that will teach you about stochastic and signal systems.
Solar cells, that's my class. I designed this class when I moved to Berkeley from industry, since there were no classes in Berkeley about solar cells. It's a great class. The requirements are 16A and B or physics and math, so you all can take it. I teach everything from the ground, semiconductors, all the way to some strategics on how to get higher efficiencies in solar cells. It's no finals, a project at the end. It's a cool class.
Do they make cranberries? Do
They
drink
make, yeah, everybody makes, I actually take students to my research lab to test different technologies, solar cells, and we all make a solar cells that is based on cranberry and not cranberry, blackberry and raspberry juice. It's pretty cool.
Solar cells from raspberry juice.
It's lovely, yes.
Think about that.
Yeah. EE143, when I'm not teaching 16A, I also teach that class. It's a great class, very current for as far as industry goes at the moment, because there you go in a clean room and you learn how to process silicon wafers to make silicon-based devices, both MEMS devices, but also transistors, capacitors, and you go through, you get a wafer that is just silicon at the beginning of class, and at the end you measure devices. It's a much smaller class, so it's one TA for 8 students, so you really get to learn really well. And this is a class that you can actually put in your CV, that you have clean room experience. And only Berkeley offers this.
Yeah, the other thing that Berkeley offers is actually a tape-out class.
A tape-out class, yeah, which it's great to be taken either together or after this, or the tape-out class is, industry is watching and financing that class, actually. What is tape-out? So when you come up with a design for your circuits, first you have a design, you create a model, like I told you at the beginning of module 2. You have a design, a model for your device. You run simulations to make sure that your device is performing the way you want, or your circuit is performing the way you want. And then you send your design to the factory. That's called tape out, because the design used to go on a tape, so you would send the tape out. And then the factory, the fab, the silicon fab, will run your design through the steps of fabrication. And then you receive back your wafer and you get to measure it. It's amazing. Never done in undergraduate studies anywhere, only at Berkeley. And that's also done by amazing instructors, Chris Pister, Bora, and
also Ali.
Ali Niklejad, yeah. So amazing class.
So you think about it, you design a microprocessor, you design radios, you design ADC, analog to digital converter, and the opposite, and you make a whole system that you send, you get the chip back, and then you get to test it, which is unbelievable. Now, in order to get that, 16B, 105. And then after that, you can take integrated circuits and so forth. Yeah, 140 and 142. Yeah. So you can get to this level. This is almost a guaranteed job. This is a guaranteed job.
The guaranteed job. You take that class, you have a job. Well-paid job. I told some of you that if you can code and you know hardware, you get the best jobs.
Okay, I'll let you talk now. Keep talking, and then I'll talk about research when you leave, when you finish.
You were going to do your research last semester? You always give me like 2 minutes at the end. Here, we talk about research. Why? Because you guys came to Berkeley. Berkeley is a research institution, and you should try to do research. And I know sometimes it's hard to navigate, and how do I get to do research? Try. Talk to the professors, go after the professors, and make sure that you have at least 1 semester of experience, just so you get the flavor and you decide if this is something that you like or not. Can you play the video? I work on flexible electronics. My group does research on flexible electronics. What is that? So here is an example of what flexible electronics is good for. So it's electronics that's is fabricated with different materials that are not necessarily based on silicon and conventional semiconductors. It has been taken off, especially on the display business, because displays break. And the viewing angle in this place is quite bad if your screen is flat, right? So here you can see that this was produced at Samsung, not in my lab. But you see how even though you're bending and the display has been abused by a hammer, it keeps working and you get much better viewing angle. And the other advantage is that it's very thin. And once it's very thin, it's also very lightweight, so it's way better to have, if you have to carry things. Okay.
You can do it.
Next, I can do?
Yeah, just.
Okay. All right, so over the years, in my group, we have been applying flexible electronics, this idea of having electronics that are designed specifically for a cause or a problem. And we applied a lot of our work for large area sensing. We have done image sensors that are flexible and based on this technology. We have demonstrated a lot of sensors that go in the body to monitor vital signs. And we are currently still working in this area of medical devices for testing bodily fluids, like Mickey was talking about testing blood. We also work on power sources, mostly because if you want to have a system that is completely flexible, lightweight, and conformal to the body, you need to think about the batteries, because the batteries are always heavy, occupy a lot of space, and they are most often the most expensive part of the system. So, yeah, one semester, a couple of years, I had very stylish students doing PhD in my group. One worked on the flexible battery, the other one on solar cells, and they came up with this piece of jewelry. That's where the glass that you see in the middle, the colorful part, is the solar cell. And the wire is actually a battery that is recharged by the solar cell. At least once a year, I get an email asking where I'm selling this, on how I'm selling this, because people like the look of it. But the important part is that it worked really well. One part of my research that I brought from my experience working at Xerox for many years is the printing part. And with lots of materials being developed, we have many materials today that have electronic properties. They are conductors, insulators, or semiconductors, but they can be processed like an ink. And once they can be processed like an ink, that means that you can fabricate your devices with printing technologies, just like the graphics industry uses printing technology. So in my group, we have many printers in my lab. And we have screen printers like silk screen, like we write Berkeley on our hoodies with silk screens. We have blade coating, inkjet printing, and all the printing technologies. So students that do research in my group are characterizing electronic devices, they are characterizing electronic properties, but they are also learning a little bit of chemistry because they have to make the solutions and see how they can print, deposit those inks that do have electronic properties in a way that makes the device operate well. So here's just another example. This was a collaboration that we have with UCSF, where the doctors wanted to monitor the formation of blood ulcers in the skin. That's important for patients that have diabetes and that their skin gets bruised very quickly, and also patients that are just laying in bed for prolonged times. And the way that this is monitored today is like a nurse goes and looks over in the skin and says, oh, it's a bit purple. Oh, it's a bit...
That's your slides that move automatically.
It's a bit, and here we've shown that if we put these electrodes that were all printed and flexible on the skin, we could predict the formation of blood ulcers 2 days before the blood ulcers actually started for patients in bed. So this is currently in a medical study at UCSF. Yes, so the idea is to... don't break your iPad. The idea is...
It's flexible.
That one is not flexible.
Oh, yeah, that's right.
Flexible, the Kindle is a flexible display, by the way. Okay, so the idea that we have been pushing is instead of having electronics and medical devices be one size fits all, right? Have something that is really conformal and designed for the specific needs. Over the years, we have shown the blood ulcers, and here you can see how it looks like a Band-Aid. We have shown devices to measure pulse and blood oximetry, which are used in wearable devices today. And in the first class of Module 2, I showed you the EMG to measure movement on the muscle. And of course, my favorite collaboration was an MRI, because when I came to Berkeley, I gave a talk, and Mickey went running. Do I have that slide? I don't.
No, don't.
Running behind me saying, Anna, do you think you could print coils? And I was like, what are coils? And coils in the MRI.
That was the beginning of a beautiful friendship.
It was, yeah. I should have put that slide. Yeah. My life was never the same after that. Okay, so then coils. Coils are the antennas, the RF antennas that go on the body as the patient goes to have an MRI. But it's uncomfortable, it's heavy. The design mindset is, let's design something that will last forever, unbreakable. And then Mickey and I came up with other ideas, walking around campus in the summer and having ideas, and this is what we proposed. We said, okay, if the coils have to go close to the body, why don't we print the coils on t-shirts? Everybody here knows the size of the t-shirts that they need to wear. You go to the hospital, you say, okay, I wear small, get a set of coils that fit me really well. Then the first demonstrator that we had was this. This is Baby Hope. She lives at the Stanford Children's Hospital now. And we designed a coil only with 2 elements for a newborn. And then the doctors at Stanford Children's Hospital liked it so much, they started using even in babies that were much bigger. This one was a 10-week-old. Then we went on and designed the bigger one that it's here with the dinos, as you can see, that it fits 5-year-olds. And the cool thing here is that typically the doctors put a respiration sensor on the kids, right on their lungs, because they're worried about collapsing the lungs with the weight of the coil. And when they got our prototype, it's so light, so nice, they put the respiration sensor on top of the coil. So, mission achieved, yes. You're going to show what we did since?
If it answers to...
Yeah. I'll keep talking. So then the doctor, our collaborator there, who kept saying, oh, can I have more coils? Can I have more? They called this the Berkeley 12 because they had 12 channels, 6 in the front and 6 in the back. And Mickey and I said, okay, let's start a company then, because we wanted the kids to have access to this technology. That's,
when it doesn't work, it doesn't work. Huh?
The Wi-Fi, yes, the Wi-Fi is problematic. So, you guys all, so we started a company, and last December, the company got approval from FDA to sell. So actually, Mickey and I, our collaboration has not been only here in 16A, has been years of collaboration, and we even have a business together that helps kids based on what Mickey knew a lot of, which is MRI, and he doesn't hide his love for MRI, and what I knew a lot, which is flexible printed electronics. This is the result. This is how our product looks like. So cute.
I know, right?
I know. We did it, Mickey.
Yeah.
Yes, we should keep working together. We're a great team. Then, okay.
You see, are they clapping because of that, or because of me actually being able to put an image on the screen?
What did you say?
I'm not sure if they're clapping because of me actually being able to connect that to the screen.
It's,
That's pretty. I just like switch the phone and it's like I just like put it.
Okay. Now my group also, and we kind of have to change our research directions every now and then, or I try to change my research directions every 8 years or so because I like to learn new things. Now I have many students working in my group on chemical sensors for agriculture because I learned that agriculture has a huge problem of contamination of groundwater due to nitrogen leaching through the soil to groundwater. And the process of fertilizing fields is so crude, they just over-fertilize everything and hope for the best. And the yield in agriculture is very small, or smaller than it should be. And of course, we need food. So I thought it was a good problem to work on. And in the end of the day, my students still work on electronic inks, printing technologies, characterization of devices. But now we collaborate with plant people and with environmental scientists, and we are learning new things, which is very exciting. And one of my students and I are going to open another company to commercialize this. Yes. You know, I like the commercial stuff too. Creates jobs, good products.
That's
yeah?
right.
All right. See?
You see,
I left time for you to talk.
Well, it
so
was designed.
how do you get involved? If you like this type of things, I always have an open invitation for students to come to my group meetings. My group meetings, some of you came to my group meeting this semester. I have many former 16A students doing research in my lab. So you just let me know that you're interested, and I will tell you when the group meeting happens, and you can come. I'm also happy to give you a tour of the lab if you want to see how a research lab looks like. Oh, you have your own.
I have my own microphone.
Yeah, go for it.
Do you want to hear a little bit what I do?
No, nobody knows what you do because you never mentioned.
That's right. I work on MRI. But I'll show you a couple of things that are interesting also in the context of this class. So you've seen the case of overdetermined systems where you have A times X equal B, but you have more equations unknown, and one of the way to solve it is using least squares. You find the closest solution that fits the data, right, within the column space of the matrix A. Now, if you go back to tomography, I didn't say tomography today, but now I'm going to say, we had this situation, remember, where we didn't have enough measurements. Like we actually made 4 measurements, but then we realized, wait, there's actually one of them is redundant, and in that case, there were infinite solutions. So you made all these measurements, you have infinite solution. The question is like, well, hold on. I mean, I did make measurements. Can I still make an image? I mean, there's infinite solutions, but maybe I can still make an image by thinking about, well, I mean, not all images, I mean, not all possible solution would necessarily look like an image. Maybe they look like crap, or they look like noise, or look like something else, but they don't look like an image. We know when we look at something, does it look like an image? Yeah, we can figure that out. Maybe we can also let a computer do that somehow. And so the cases where you have an underdetermined set of equation, you've got some A times X equal B, and now you in this class would tell me, oh, there's infinite solution, you know, I cannot find a single image that fits that. And I could tell you, well, I mean, well, can you at least find one that's reasonable? Maybe, or maybe a couple or a few, that would still give me some information that I can maybe use to diagnose that poor patient that we didn't collect enough measurements on. So that's kind of the question that comes in mind. And so my lab works in the area of computational MRI. It's kind of the marriage between you know, computers and computation, and also the physics and the modeling, to look at all this, you know, from the hardware to the physics, to how you change the data you collect, and how you reconstruct images or something, information from the data you've collected. You can also control how the data is collected. You put it all together, and you can instead, I don't know if you've seen MR images before, but they usually are static. But now you see kind of things are moving, changing, flowing. That's because you can leverage computation, you can leverage modeling in order to get more performance. So that's kind of the area of my lab. But a lot of it is related to the fact that, you know, there is this thing called image compression. I mean, obviously, when you take a camera, and you can take pictures, and if you actually look at the amount of raw data you get from the camera, it's pretty large. It's like it'll be, you know, tens or hundreds of megabytes sometimes, okay? But then you can go and you take those hundreds of megabytes and then you compress it, and like it's tiny, it's 2 megabytes, it's, you know, 6 megabytes, that's it. Where does all these megabytes go? Why do I actually need to collect all this data, right, in the first place? So that notion is very interesting. So if you actually look at image compression, this is, you know, two pretty girls. Now they're 15. They were not 15 then. So if you look at a non-compressed image, you know, this is size 36 megabyte, compressed 2 megabyte. You get 18 times compression ratio. Somehow, magic, JPEG, some do that, and you cannot see the difference with your eyes. You cannot see the difference. So okay, where's this data I went through? Now you look at, you know, 20. This is April 20, 420, on campus. This is the video, right? I mean, what the heck is going on there? Well, actually, from an information point of view, we got this like high definition video, 30 frames a second, 3 kilometers, 54 seconds. That will be like 10 gigabyte. But, why? Okay, it's 10 gigabyte, but when it's compressed, it's only 71 megabyte. I mean, it's 140 times compression. Obviously, Netflix, HBO, you know, all those folks that do streaming video, they leverage that. They don't send you, you know, 10 gigabytes per minute to your, I mean, that will not be possible. Right? So some redundancy, right? Because, I mean, there's not a lot going on there, right? Well, I guess there's a lot going on, but not a lot there. Every frame is similar to the other. It's not very different. There's a lot of redundancy there, right? Same with MRI. MRI, you collect data. It takes you time to collect data until you produce an image. And so if you try to look at, let's say, contrast injection through a body of, let's say, a pediatric patient, you just won't be able to see that. It's just too slow. So what you could do instead of collecting all this data in MRI, you can kind of subsample it, collect a subset of the data, but then knowing that it is compressible, maybe you can then go and say, you know what, among all possible infinite solutions, maybe you will find the one that's kind of maybe the simplest, the most compressible. Maybe that would then give me an image that would be something reasonable. And this is the stuff that we've been working on. And then when you can do that, well, then you can make those videos. You know, you can go faster imaging, or instead of faster imaging, and this is, again, pediatric patient that injected with contrast. Contrast goes through the heart, goes to the lung, goes back to the heart, then to the body, then back to the heart and the lung and the veins and something like so on and so forth. So it's pretty complex. But then maybe you can also get extra information like flow, you know, inside the heart, and be able to see, for example, this particular patient is a congenital heart disease, so you can actually see what's going on inside. I'll just finish with that. So here's kind of like an idea of, you know, reconstructing an image which, you know, doesn't have all the data. It looks pretty crappy, non-diagnostic.
Can you enhance the image from here?
Can you enhance it right here?
Can you enhance it?
Can you enhance it?
Can we enhance this?
Can you enhance it?
Hold on a second, I'll enhance. Zoom in on the door. Image enhancer that can bitmap?
Maybe we can use the produce send method to see into the windows. This software is state of the art.
The eigenvalue was off.
With the right combination of algorithms, he's taken illumination algorithms to the next level, and I can use them to enhance this photograph.
Lock on and enlarge the z-axis.
Enhance.
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 Freeze and enhance.
Well, you get an enhanced image. This is Hollywood stuff. But you know, using actually certain algorithms that leverage this sparsity idea, you can go from this really crappy image into something that looks like this, and now this is diagnostic. And I would say this is about a decade-year-old result. So now the results are even better. So with that, maybe we have like a few minutes for questions, and then after that we will say goodbye and see you in the
solar cell class.
office hours or solar cell class or the final. And
On the final, yeah.
And all sorts of,
We are proctoring.
or
the
just
final.
around. Don't be strangers, by the way. Say hi. If you see us, even if you don't remember, we just go and wave and smile. But you can also approach, it's like, hey, I take 16A with you. It's like, oh, cool. How do you like it? It was like, oh, I didn't really do well.
"Woo."
And I was just like, oh, I'm sorry. I hope it's not because of
Oh,
us.
I
No, you were
failed.
terrible.
Yeah.
That kind of stuff. Yeah, it happened, by the way.
But we will be there also on the stage when they graduate and high five.
Oh, that's
them.
right.
Yeah,
We'll
yeah.
high five you when you graduate,
Yeah,
if we make it.
it always hurts. Yeah. You don't have Tiffany's slides there?
I don't.
Okay. I'll post it. There is a set of slides that Tiffany, who is a person who cares very much about undergraduate research opportunities on college. Tiffany read them. So if you haven't met her yet, make sure that you do. She's wonderful, wonderful. And I asked her for her slides on how to get involved, how to apply to programs. You can, if you know you like research and you want to do research, there are several programs that you can apply where you go to another university to do research during the summer, which is pretty cool, RU programs. And she knows all the requirements for each program, and that's a good way of you being Berkeley ambassadors somewhere else. We always receive students from other universities here during the summer. So if you are doing research in a lab here, you might also collaborate with someone that goes to UT Austin or any other universities that have collaborations with us. She also knows a lot about fellowships that you can apply so that you get some money while you're doing research, and programs where you get to present your research results to industry, and that has been a very good way of undergraduate students getting internship jobs during the summer based on what they are doing at Berkeley. So look for her name and go and say hello to her. Tell her that I sent you, and she will know. We are always looking for students that really want to do research, and we try to place the students in different research groups. It has an A.
Yeah, what?
An A. Yeah.
That's an A.
Okay, yeah. So she's really, she will try her best
You can't read
to
non-cursive.
connect you.
You can't read non-cursive.
I can. She will make her best to connect you and when you get a research opportunity, most important of all, show up. Okay, show up every day. There is a group meeting. You're there. Your mentor, which will most likely be a graduate student, says, "Oh, let's work in the lab tomorrow." You are there. Okay, and you will get the flavor of Berkeley that way. There's no grades, no points, just knowledge and experience. Yes. Homework 13, yes. When I say, don't worry about grades, learn, you ask me about homework. What's the question?
Even if people are dropping this homework, there's an extra credit question there. So if everyone fills out the survey, they could get 2 points in the final. Just wanted to advertise it.
Oh, he